Okay, good afternoon friends. We are discussing about poles and zeros, location of poles and zeros and determination of residues. Suppose we have a function ZS S plus A1 into S plus A2 divided by S plus B1 into S plus B2. So, this type of function, or maybe S plus B3 also. When we make partial fraction of such functions, it may be just the response function, or when ZS is there, if you give an impulse input, then this itself will give you the output function. So, any function of this kind, when we want to measure when we want to calculate the residues A1, A2 etc., we computed, say A1 we computed like this function ZS multiplied by S plus B1 and then evaluate this at S equal to minus B1, is it not? Now, this B1, B2, B3 they can be complex conjugate also. If they are complex conjugate, they should be in pair, conjugate pairs. Okay. So, ZS into S plus B1, S evaluated at minus B1, I mean by putting S equal to minus B1, evaluate A1. What does it mean? If I multiply by S plus B1, this will go ZS into S plus B1 means this we are evaluating at S equal to minus B1. So, suppose you are having B1 is here, B2 may be here, okay. A1 may be here, A2 maybe its complex conjugate, A1, A2 both could have been real also. Similarly, there can be A3, A4 and so on. So, ZS into S plus B1, when we are evaluating at this point, that means I am placing S at this point, is it not? S is minus B1. So, from here, last time we were talking about any location of S, what was this vector representing at any S? S plus A1. If it is from the 0, it was representing one of these numerator factors. S plus A1 was this, S plus A2 was this. So, this is S plus A2. Similarly, S plus B1 is this, S plus B2 is this. When I am taking S itself at minus B1 and then measuring these distances, so this will be S plus A1 at S equal to minus B1. Similarly, S plus A2 and this is S plus B2. Okay. Had there been another point minus B3, then from here to here that will be S plus B3. So, let us take a few concrete values of A1, A2 etc. and then evaluate S. Therefore, suppose we have sorry, this is at minus 1, this is at minus 3, this is a 0 and this is a 0. I have got S plus A1 into S plus A2 by S plus B1 and say another one at minus 4, S plus B2 into S plus B3, where A1 is minus 1 plus j, A2 is minus 1 minus j, B1 is equal to -1, B2 is -3 and B3 is -4. So, if I write this as equal to A1 by S plus B1, that is S plus 1, I am interested in calculating A1, then this is S plus A1, this is S plus A2, this is S plus B2, and this is from 4 to 1 S plus B3. All right, all evaluated after multiplying by B1. So, this one will not come, okay, and then we are evaluating at S equal to minus B1. This is what we are interested in. So, how much is this? The numerator distances are, how much is this? This is 1 in magnitude and angle of minus 90 degree. So, 1 minus 90 degree. What about this one? 1 plus 90, okay, divided by, this is magnitude 2 and an angle of 0, it is horizontal, and this one is 4 to 1, 3 angle 0. So, how much is this? 1 by 6 and an angle of 0. Okay. So, vectorially also you can calculate these residues A1, A2, A3, A4. Okay.
So, this is one of the better methods.
Well, geometrically you can always construct and see the residues. Okay. If you can evaluate these vectors quickly from the position of the poles and zeros, then the calculations sometimes become very easy. Now, let us investigate what are the possible location of poles and zeros, possible locations of poles and zeros of a driving point function. A driving point immittance function. What do you mean by immittance function? It is either admittance or impedance, a general GS, ZS or YS function. There are some common properties both of them should have. So, what are those properties in terms of poles and zeros, locations of poles and zeros? What could be the nature of poles and zeros? Now, when we apply a voltage, measure the current from the sending end, then V1 by I1, it can be a two-port network also. When this is kept open, this is called Z11. Okay. When I am keeping it open, it is the impedance seen from this side. All right. The impedance seen from this side, what will be the property of this? We are talking about network elements which are passive in nature, RLC. Okay. So, what would be the nature of Z11S? Suppose Z11S is S plus A1 into S plus A2 divided by S plus B1 into S plus B2, maybe S plus B3, maybe S plus B4 and so on. Can it be a driving point impedance or an admittance? Is this possible? Any function of this type, can it be a driving point impedance or admittance function? Or is there any scope for a negative term, say S minus A3? We would like to examine that. So, before that we would like to see the response. Suppose we excite it by an impulse function of voltage, then Vs equal to 1. Suppose Ys is given, this function is a Ys, okay. Then what will be Is? It will be Ys itself, Ys into 1, is it not? So, if Ys is written in a partial fraction form, and so on, then what should be the current IT? What should be the current? It will be A1 into e to the power minus B1t and so on, exponentially decaying terms. Had I had minus B1 term or minus B2, then it will be e to the power plus B1t or B2t. That means the current will exponentially increase. Is it possible physically to get a current by applying just an impulse voltage? You just apply a voltage and withdraw it. Can you have a situation where the current will continuously flow through that and it will keep on increasing? It goes against the principle of conservation of energy, is it not? So, it cannot go up, it can only die down, all right. So, from the conservation of energy principle, the factors will be of this type, not S minus B1 or S minus B2. What does it mean? S plus B1 means the roots B1, B2 etc. should be in the left half plane, all right. Suppose you have a complex root, suppose B1 and B2 are say minus alpha plus j omega minus alpha minus j omega, that is also possible. So, you will get A1 by S plus alpha plus j omega plus A2 by S plus alpha minus j omega, where A1 and A2 will be complex and they will be, it can be shown they will be complex conjugate, okay. Otherwise, if you add it together, the numerator will not be all real coefficients, okay. So, if you are having a network function which is a polynomial in the numerator, a polynomial in the denominator, which have been written in the factored form, and if the polynomial coefficients are all positive, then they must appear, if they are complex, they must appear in conjugate pairs, all right, number 1. Number 2, if you make partial fractions, then A1, A2 will be complex conjugate, it can be proved very easily. So, if I combine them together, they will be giving rise to some e to the power minus alpha t sin omega t plus theta. So, that will give me a response like this, which will be dying down if it is in this form. Had alpha been here, that means if you have roots with the real part on the right hand side, then this will become plus alpha t and that will be causing a divergent oscillatory function, all right. So, it will keep on increasing. Can you have a situation when it will keep on increasing, the current will keep on increasing and oscillatory when the voltage has been withdrawn? Again, that is not possible, it will be against the principle of conservation of energy. So, the poles of Ys must lie in the left half plane, left half of S plane. We are talking about the roots in the S plane. By the same argument, if I give an impulse of current and measure the voltage across the terminals, if I can give an impulse of current, that is 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 1 and what will be the output? Zs into 1, that will be Vs, okay. So, Zs is nothing but 1 by Ys, So, S plus B1, S plus B2 will go in the numerator, S plus A1, A2 etc. will come in the denominator, and by the same logic, if I apply an impulse of current, I cannot expect the voltage to build up indefinitely. Okay. So, the roots A1, A2, these also should be in the left half plane. So, that means both poles and zeros of ZS or YS should lie in the left half plane. This is the first criteria for a driving point impedance or admittance function. So, one by one we will list out the properties of the driving point immittance function. So, one is poles and zeros must lie in the LHP in the S plane. Okay. Is it possible to get roots on the imaginary axis, poles and zeros on the imaginary axis? If you have, say, at some omega 1 a pole like this, that means YS or ZS has roots like this, S squared plus omega 1 squared into S plus B1 and so on. One factor is say S square plus omega 1 squared. This will result in a term like sum AS plus B by S squared plus omega 1 squared. Okay. Once again you apply an impulse. Okay. If you apply an impulse of voltage, and if this is the admittance function, voltage into admittance, that will be giving you the current. So, one of the current terms will be, this will give me some C sine or cosine omega 1 t plus theta, this kind of a term. Okay. So, it will be giving you a current which may be oscillating. It is not building up, it remains a steady oscillation, that is possible. Theoretically, if you have an LC network, you will have a sustained oscillation. So, it can have an oscillation like this, we call it a stable system still. Is it possible to have multiple roots on the imaginary axis? If you have, instead of S square plus omega 1 square, if you have squared term, then what happens? If you have a squared term, then there will be a term like S plus B S square plus omega 1 square plus something in the numerator by S squared plus omega 1 square whole square, whose inverse will give you t into sine omega t plus a theta dash. Other terms are there. Okay. So, this term will give me t is function like this. So, it will go on increasing. Is that all right? So, such possibilities are ruled out. By the same logic, in the zeros also, in the case of numerator also, you cannot have multiple roots on the imaginary axis. So, zeros and poles and zeros on the imaginary axis must be simple. On the imaginary axis must be simple. Okay. Another thing, when we talk about RLC elements, see both these admittance and driving point admittance and impedance functions, they are after all obtained by some combinations of network elements like this. Suppose you want to measure Z11 driving point and impedance, then keep it open and then measure the impedance, is it not? While measuring the impedance, you take this plus this and parallel combination of this and so on. Now, these elements are R plus some Ls plus some 1 by Cs, this kind of additive elements or series parallel combinations of these. So, when you make repeated conversions, say from star to delta or making parallel combinations of such elements, it is all positive terms like this, and their say parallel combinations, that is products, and then again you divide by some sum. In no case there is any scope for a negative sign. Do you get my point? So, after making all these combinations, the numerator and the denominator will always have positive coefficients. So, if I write Z11 S as some Ps by Qs, then this will be, if I write in a polynomial form, some A0 plus A1s plus A2s squared and so on, divided by B0 plus B1s and so on, say A m s to the power m plus B n s to the power n. Okay. So, all the coefficients A0, A1, A2 etc. and B0, B1, B2 etc. must be positive. Is that all right? So, all the coefficients of Ps and Qs where coefficients of polynomials Ps and Qs, where Ps by Qs is the driving point admittance or impedance function, must be positive. Okay. Can you have, by any states of imagination, by combining Ls, 1 by Cs, R etc., can you have polynomial where you get a fractional power? So, it has to be a rational polynomial, s to the power 1, s to the power 2, you cannot have s to the power 2.5, alright. Similarly for this, okay. This is also another point, these polynomials must be in integral powers of s. Can you have an impedance, say what can be the possible difference between m and n? Suppose n is 5, then what could be the possible value of m? So, suppose s to the power 2 is the last term, I get a2 s2, a0 plus a1s plus a2s squared divided by b0 plus b1s plus up to b5 s to the power 5. Is it possible to have this type of network function, driving point impedance? Let us make s tending to infinity. S tending to infinity means this will be negligible, it will tend to a2 s squared and this will tend to b5 s to the power 5. So, when s tends to infinity, this tends to a2 by b5 s to the power 3. Now, can you have an impedance which is represented by 1 by s to the power 3? When you take a very large value of inductance, large value of s, then all the inductive elements will be offering highest impedance and all the capacitive elements will be shorts. So, by any states of imagination, say you take capacitive values as shorts, so you do not ignore the capacitive elements, alright, and you are left with only inductances. So, what is the, all these elements will be consisting of either a short circuit or an inductance, alright. Now you have, suppose they are having, all of them are having LC, LC, LRC, etc. So this is an inductance, this is an inductance, this is an inductance, this is an inductance. So overall combination will tend to be another inductance, and that cannot be 1 by S cubed, it can be only LS. Okay. So the difference should be such, it cannot be, it cannot terminate in S square. Can it be S cubed? Then also it will be ending in 1 by S square. There is no element which can give you finally a value like 1 by S square. Is it possible to get A4 S to the power 4? Then it will tend to 1 by S. Yes, that means the entire network is tending towards a capacitive element. Okay. So it can be S to the power 4. Can it be S to the power 5? So S to the power 4 is possible. Can it be S to the power 5? It can be a ratio, a constant, that means it will tend to a resistive element. Can it be S to the power 6?
Yes.
Then it will tend to an inductance. Alright. So S to the power 4, S to the power 5, S to the power 6, these are possible. That means if I have the maximum power of this as S5, this can be either 4 or 6. That means difference in the maximum power of the polynomials, the difference can be at the most 1. Okay. That is m minus n or n minus m, that is m difference n can be 1 or 0. Okay. So if this is S to the power 5, it can be 1 less or 1 more or equal. The difference cannot be more than that. Is that all right? So next property is the difference in the degrees of the polynomial must be restricted to 1, must be at the most 1. Poles and zeros must be simple on the imaginary axis, the coefficients must be positive, difference in the degrees in the polynomial must be restricted to 1. Suppose we have one term missing, that is it possible that A1 is 0? Can there be a missing term in the polynomial? So suppose PS is A0 plus A1s plus A2s squared plus A3s cubed and so on. If one of the terms is missing, then what happens? Does it ensure all the roots lie in the left half plane? No. So to check whether all the poles and zeros lie in the left half plane, we have a criteria, Routh or Routh's criteria, which states that all the coefficients must be present, all the coefficients of PS, any of the polynomials, because we want to ensure both PS and QS should have roots in the left half plane. So all the coefficients of PS and QS must be positive and non-zero. Any question? There can be an exception. We will come to that exception later on. Can you suggest where it will not be necessarily, it is not necessary to have all the coefficients present? No. Suppose alternate terms are absent, that means either it is an even function or an odd function. See, a squared plus omega square, if it is a factor, that means what? It is an even function. So, for such cases it is possible, and that will come to that will give you an oscillatory term. That is, for LC network, for example, you will have functions zs or ys where you will get a square plus omega 1 squared, a square plus omega 2 square, and so on, and one will be even, the other one will be odd. That is possible. That is an exception, that is alternate terms are absent. In that case you can have this will be violated. So, for the general case all the coefficients must be positive and non-zero. And the second criteria is you make a table, you make a Routh array, and from the table of that from the column you can see the positiveness of those terms and decide whether you can decide whether it is a stable system or unstable system, that is whether all the roots are in the left half plane or right half plane. So, let us write the table. Suppose you are having a0, a1s plus a2s squared etc. as the polynomial an s to the power n. Say. You start with the coefficients a0, alternate coefficients a2, a4 and so on. Then next make the next row with a1, a3, a5 and so on. Next a1, a2 minus a0, a3, so a1, a2 minus a0, a3 divided by a1. Similarly, a1, a4 minus a0, a5 divided by once again a1 and so on, you make another row. So, these synthetic rows you generate, again you take this and a3 minus a1 into this quantity divided by this quantity itself, that will be the new element in this row, similarly another element and so on. After completing this, you check the signs of the first column. This is positive, this is positive, this is positive, this is positive. If all of them are positive, then the roots are in the left half plane. All the roots are in the left half plane. If you find there is a sign change, the number of times the sign is changing here will give you the number of roots lying in the right half plane. So, RH criteria, Routh-Hurwitz criteria must be satisfied by PS and QS. Another point I just forgot, ZS or YS, if it is written like this, A0 plus A1S and so on, B0 plus B1S, can the last term be absent? Say either A0 or B0, is it possible? Can we have a situation like this, A1S plus A2S squared, suppose we have A4S4 divided by B0 plus B1S plus say B5 S to the power 5 or maybe B4 S to the power 4. is it possible to have the first term absent? Is it possible? That means the first coefficient A0 absent. Okay, let us see. When S tends to 0, S is very, very small. So, it will tend to the lowest order term in S, and that will be equal to, so limit if S tends to 0, this will be A1S by B0. It will be something like an inductor. So, it will tend to be an inductor. It is possible. Similarly, in the denominator, can B0 be absent? A0 is present, say, but then can B0 be absent? Similarly, A0 plus A1S A4S to the power 4 divided by B1S plus B2S square and say B4S4. Is it possible to have this term B0 absent? Once again you put S tending to 0, it will be tending to A0 by B1S, it will be tending towards a capacitive element. That is also possible. So, the last term either of the numerator or of the denominator may be present, may be absent. If both are absent, A0 and B0, then you will be able to take one S common here, one S common here. So, those two common S will get cancelled. So, this is the next property, that is the polynomials can have either the numerator or the denominator polynomial can have the last term, or the here it is the first term absent. Given this, what would be the next condition? Suppose we have all the poles and zeros in the left half plane. Is it a realizable function? Can you realize it? So, if I have a function S plus 1 into S plus 10 divided by S plus 2 into S plus 3. Can you realize this? Is it possible to realize? Both the poles and zeros are in the left half plane. Let us see what it will look like. A by S plus 2 plus B by S plus 3 plus C by plus C maybe, okay, a constant. So, how much is A? If I make S plus 2 equal to 0, so this is minus 1 into 8 divided by plus 1, so minus 8, okay. B by S plus 3, if I multiply by S plus 3, this will be minus 2 minus 1, so it is 14, okay. C, if I make S tending to infinity, this will be 0, this will be 0, so it will be S squared by S squared 1. So, this thing can be written as minus 8 by, suppose this is ZS. Can I break it up into form like this? S plus 2 plus 14 by S plus 3 plus 1. This is ZS. Is it realizable? This is having a negative coefficient. I have seen we have seen earlier, all RC combinations will give me positive terms. Here it is minus 8 divided by S plus 2. So, this is not realizable. I am bringing them to very small simple form, okay. 14 by S plus 3 plus 1. This one I can realize as 1 ohm resistance. 14 by S plus 3 I can realize by RC combination. You put S tending to 0. So, S tending to 0 will be blocking this capacitor. So, 14 by 3 is the resistance. Make S tending to infinity, it is 14 by S, that means 1 by 14 farad. So, this is an RC combination. This is a 1 ohm resistance, but I cannot realize minus 8 by S plus 2. It is not possible to realize by RC elements. Okay. So, I would like to know whether it is possible to realize this. Okay. So, ZS, if it is given to you, it can be YS also. The general property we want to extract for ZS and YS from a given function, so that it is realizable. I give a voltage, an impulse voltage, and then I withdraw it. That means the source is retained here, okay, an impulse of current say, and then the current through this is allowed to flow. Okay. I have an impulse of current, and then it is shorted, so that the current is maintained. How much will be the energy? How much will be the energy of this? If I apply any sinusoidal quantity, sinusoidal input, then what will be Z j omega at any frequency? I can put S equal to j omega. Z j omega will have a real part and an imaginary part. Okay. Now, if I put S equal to j omega, if there are S squared terms, it will be j squared omega squared, that will be minus omega squared, it will be real. So, all the S squared, S4 terms will be real, and S cube terms will be imaginary. So, real part will correspond to the even part of ZS, and the odd part will be, if I put S equal to j omega, in the odd part I will straight away get the imaginary part. Is that all right? Is that okay? Now, I excite ZS by a sinusoidal source, Vm sin omega t, any frequency. Then how much will be the power, active power lost? I squared into real part of Z. Is it not? That means ZS at S equal to j omega, I can write as some R plus jx. Okay. So, it is I square into this R, which will be the power, and that has to be always positive. Okay. I square is a positive quantity. That means the real part of this for any omega must be positive. Is it all right? Real part of ZS, Z j omega, is nothing but even part of ZS evaluated at S equal to j omega. Is that okay? So, let us evaluate what is the even part. So, if you have ZS equal to M1 plus M2 by N1 plus N2, where M1 and N1 are the even parts, even functions, and N1, N2, sorry, M2 and N2 are the odd parts, okay, then Zs can be written as m1 plus m2, I will multiply by n1 minus n2 both sides. So, that denominator will become n1 square minus n2 square. Okay. Is that all right? So, the numerator is m1 n1 minus m2 n2. This is even into even, minus odd into odd is even into even is even. This is an even function, odd square, even square minus odd square will also be an even function. So, even function divided by another even function plus m2 n1 minus m1 n2 divided by n1 square minus n2 square. So, this is the odd part, this is the even part. Okay. And this has to be tested for s equal to j omega. If I put here, it must be always positive, because that represents the resistive part, that represents the power consumed part, is it not? Now, n1 squared minus n2 square, let us see, n1 plus n2 into n1 minus n2. So, n1 plus n2 is say p plus jq or some a plus jb, capital A plus capital JB. Then n1 minus n2 will be a minus jb, because it is the odd part which is becoming negative. So, it will become minus jb. So, it is only the imaginary part which will become minus, is it not? So, a plus jb into a minus jb is what? A square plus b square, that is always positive. So, the denominator is always positive. So, I have to test the positiveness only of the numerator, is it not? The denominator is always positive, is that all right? So, let us take an example, it will be clear. The same example, s plus 1 by s plus 10 divided by s plus 2 into s plus 3. So, this is Zs. I will write this as s squared plus 11s plus 10 divided by s squared plus 5s plus 6. So, what will be the even and odd part? S square plus 10 is the even part plus 11s, this is the odd part. Similarly, s squared plus 6 plus 5s. Okay. So, m1 n1 minus m2 n2 is to be tested for positiveness, because the denominator is always positive, that is what we have ensured. This square minus this square is always positive. So, m1 is s squared plus 10, n1 is s squared plus 6, m2 is 11s, n2 is 5s. So, m1 n1 minus m2 n2 will become s squared plus 10 into s squared plus 6 minus 11 into 5 55 s squared. Okay. So, that is s to the power 4 plus 10 plus 6 16 s squared minus 55 s squared plus 60. So, that is s to the power 4, is that all right, minus 39 s square plus 60. Now, if you evaluate at s equal to j omega, what will this give you? If I evaluate this at s equal to j omega, omega to the power 4 plus 39 omega squared plus 60. Is it always positive for all values of omega? Yes. So, it is realizable, because power dissipated, if it is negative, what does it physically mean? If the real part is negative, that means if I pass a current, instead of getting heated up, it will be cooling down. Is it possible? I square R is negative means what? It is cooling down. That is not physically possible. So, the real part of the impedance function Zs, the impedance function Zs must be always positive. So, even though we have seen earlier for this example the residues are coming negative, it may not be possible to realize by RC combinations. You may try with LC, it may fail. It may be possible with RLC, alright. So, but it is a realizable function. So, if you find that this test fails, it is not positive throughout for all values of omega, somewhere it is becoming negative, then you can say it is not realizable by passive elements. This is not a network function. Is that alright? So, we will stop here for today. We will continue with this and a few simple realizations we will see with LC, RC and so on. Good morning friends. We will be continuing with driving point impedance function or immittance function. We have seen the properties to be satisfied are poles and zeros of the immittance function must lie in the left half plane, left half of S plane. Then poles and zeros on the imaginary axis must be simple. On the imaginary axis must be simple. These are two very important properties. And then to ensure that poles and zeros lie in the left half of S plane, actually all the coefficients of the polynomials, all the coefficients of numerator and denominator polynomials, we were using PS and QS, okay. PS and QS must be positive, all the coefficients of PS and QS must be positive, okay, and real. Then the difference in the degree, of PS and QS, the degrees of PS and QS must be restricted to 1. All right, difference in the degrees must be restricted to 1. We will draw a diagram. So, this is omega, because now we can take the frequency as the axis and corresponding value of x omega, x omega. How will x omega vary with omega? Let us go back to the first problem. Suppose we have just an inductance what will be its x j omega L. So, if I write this as j x L, j x L, then x L will be varying linearly with frequency. Is that all right? With a slope of L, with a slope of L. So, this is x L. What about x C? If I have a capacitor, then x C will be minus j by omega C, is j x C. So, x C is minus 1 by omega C. Is that all right? X C is always negative. So, it is inversely proportional to frequency, it will be a rectangular hyperbola varying like this. So, this is x C square plus 1. Suppose it is 2s by s square plus 1. What does this mean? If I make s tending to 0, it will be going to 2s. So, when is the admittance becoming 2s? Admittance is Cs. In case of admittances, Cs is the admittance. So, it is 2 farads. So, it will be a 2 farad capacitance. At that time, at a very low frequency, inductance is 0. It is a series combination. You see, if y1 is this, corresponding z1 is how much? S square plus 1 by 2s. That means s by 2 plus 1 by 2s. So, half Henry inductor and 2 farads capacitor will give me this impedance, whose admittance is this. So, each admittance you just invert and then separate, you will get the corresponding LC values. Is that all right? So, similarly you get another LC combination, Okay. Interestingly, these values will be different from the Foster realization, Foster 1 realization. But how many inductances were there? 1, 2, 3 and 3 capacitances. You go for this realization, you will get the same number of elements, type of elements will be of the same number, 3 inductances, 3 capacitances. So, if we go from impedance, it is Foster 1. If we start from admittance function, this is Foster 2 realization. Okay. We will stop here now, we will continue with this in the next class.